So this is like a bonus section. It's not required, but it's kind of a more advanced section for those of you to go a little further that would like to. So we're going to talk about closed pipe and open pipe resonance. The first thing we're going to talk about is closed pipe, and then in the next video we'll talk about open pipe. So we talked about resonance. Resonance is where those frequencies are vibrating and where you can actually hear sound. And so this is supposed to be a closed pipe. See, there's kind of like a bottom here. And so let's talk about closed pipes. So if you have a closed pipe, it will resonate when its length is an odd number of quarter wavelengths. So this sounds weird. So we're going to count our waves in quarter wavelengths. So let's talk about a wave again. And you remember, if we have, this is from here to here, this is one wavelength, from going up to the crest to going up to the crest again. That's one wavelength. That means this right here is half a wavelength. Okay, and if you put a half in half, you're going to get a quarter. Okay, and a quarter plus a half, which is really 2/4, is 3/4, and then the whole wavelength is 4/4. Okay, so if we look at this section of the wave right here, do you see how it's kind of opening up? And if we were going to draw it here, we could do this. And this part right here corresponds to this part right here. And so this is a quarter wavelength. And you can see the frequency is equal to, it's going to resonate at quarter wavelengths. So there could be like a 1 up here. Okay? Then here, you're not going to resonate at 2/4 because that's even. And that would be like this. Right? So this is 1/2, and then you add another one on, another quarter, and you've got 3/4. And you see you have 3/4 right down here. Now again, it's not going to resonate at 4/4 because 4/4 is even, and it only resonates at odd wavelengths. And so this pipe right here, this closed pipe, you have 1/4, 2/4, 3/4, 4/4, 5/4. And I'll draw it here so you can see it. That was really bad. But 1, 2, 3, 4, 5. So you have 5/4. And you can see the formula has 5/4 right there. So that's resonance in a closed pipe. And it's odd number of quarter wavelengths, which sounds really weird, but that's just kind of how they measure it. So again, you have 1, 3, 5. So let's try an example problem. In this example problem, you have a tuning fork that has a frequency of 440 Hertz. And we're talking about closed pipes. And then we want to know the spacing between the resonance when the air temperature is 20 degrees Celsius. And when they tell you that the air temperature is 20 degrees Celsius, they're basically trying to tell you that the speed of sound at that temperature is 343 meters per second. So that's what they're telling you. On your test, I'm not going to expect you to memorize that. So we want to find the spacing between the resonances. So here's our formula for the fundamental frequency. And they're not entirely clear what they want here. They say a spacing, and so that's like a distance. So we have a wavelength, and then we also have the length of the pipe. And so we're going to go ahead and we're going to calculate both. So if they want wavelength, which I'm pretty sure is what they want, but just to be safe, it wouldn't hurt us to calculate both. Okay, we're going to use this formula. And this can be put in the triangle, you've got speed over wavelength. So I'm going to put speed over wavelength, and then your frequency is the one that's left. And if we want to solve for wavelength, we're going to have wavelength is equal to V over F. So I'm just going to go ahead and I'm going to plug in my numbers. I have 343 meters per second. I'm going to write it like this so I can check my units and make sure they're right. And then you have 440 hertz. And remember, hertz is equal to seconds to the negative 1, so the S goes up here. And so this S crosses out, and this S crosses out. And you have 343 over 440, and you know it's going to be in meters. And that's going to be 0.78. Okay, now, if they want us to solve for the length of the pipe, I'm pretty sure that's not what they want, but I want to go ahead and work a problem with you, so kind of left it ambiguous. So we have frequency is equal to V over 4L. And we can also put that in the triangle. So we want V on the top. We can just put 4L on the bottom. We'll put both of them. Even though there's a number there, it's not going to kill us. And then we have our frequency. And we're looking for 4L. So we have 4L is equal to V over F. Okay? Now what I'm going to do is I'm going to get 4F equals some sort of number, 4L, and then I'm going to go ahead and I'm going to take the L from both sides. So I'm going to just keep 4L, and I'm going to put my speed of 343 meters per second. Meters per second. I don't know what I was thinking. Over 440 hertz. Okay, and that's going to give me 0.78 meters. These seconds both cross out. And it's 4L equals 0.78. So L does not equal 0.78. So I'm going to divide both sides by 4. And I'm going to move my math up here, which if a math teacher were to see this, they'd probably get really angry because they don't like you to do that. But so then we'll have L equals 0.78 divided by 4, which is 0.19 meters. So the length of our pipe is 0.19 and our wavelength is 0.78. Okay? So these are the two numbers that we found in this problem. And this is for a closed pipe. And some instruments that are considered closed pipe is a clarinet. This is the clarinet. I'm not a band person, but I want to say this is the marimba, and these are the xylophones, but it's pretty, I may have gotten it wrong. So if I did, just let me know, and I'll fix it. And then a she shell is also known as a closed pipe, but you and I both know that you can actually put a shell up to your ear, and you can hear the ocean. And so that's actually a closed pipe. I have a really big conch shell in my room. Ask me, and I'll let you borrow it, and you can see that you can hear the sea, although I think it's not really the sea. So these are closed pipes.